Anyway, let's have some more fun on Mohs circle. Right. So we want to determine, so the objective over here is to determine, now this is real life, okay? You see the load already, okay? We are going to determine the optimum orientation of the carbon fiber.
Sorry, are you wrapping this in carbon fiber or is it made out of carbon fiber?
You usually wrap things in carbon fiber. You don't make things from carbon fiber. I mean, there's some structure that you could, but for a shaft, you usually don't.
Right.
Okay, you usually don't. You usually find something that's lightweight, that's weak, and you reinforce with carbon fiber, right? Griffin, does that make sense to you?
Yeah, I'm on board.
Okay, so that's why you see a lot of things where people wrap around things with carbon fiber. Is there's a basic core in there. Okay, there's a core. There's a inner layer, and this inner layer is can make of very weak and lightweight material, and you just reinforce with carbon fiber.
When you say wrap with carbon fiber, do you mean like infuse it with the material, or are you just gonna use some adhesive?
Adhesive.
Wouldn't then the material be limited to the strength of the adhesive, not the carbon fiber itself?
Yes, it does. That's where the if Sean, you were to see the video that I showed last week, it's also important regarding the epoxy. Okay, the binder is also critical. Okay, so but for this to work effectively, is still you have to lay it on the principal stress direction.
Right.
Okay. Right. So we are going to determine the optimum orientation of the carbon fiber. Okay. So now I'm going to draw our transformation. So I'm going to call this my X. Okay. And then this is my Y. And this is my Z. So later on, when I draw a certain view of the shaft, you will know how we are looking at. Okay. Right. So for this case, the shaft, okay, the shaft will be reinforced. Okay, reinforced with carbon fiber reinforced plastic. Okay. So we have to do it in such a way, we have to find the optimum angle Okay, we have to find the optimum angle such that there is no shear stress or shearing stress acting on the carbon fiber. Okay, so basically we have to orientate it at the principal plane. Okay. So for this case, okay, we are going to make an assumption. So let's say, not let's say, we know that point H is the critical point. Okay. So point H or element H is the critical location where failure will occur. Now, in stress analysis, you only calculate the stress at where failure will occur. You don't spend money to calculate every point. Okay, this point I'm going to calculate. No. Okay, it is too time consuming. I mean, now you have finite element. It's not necessarily time consuming. Okay, but it's expensive. Okay, so we know that at point H, why point H will fail? For example, point H is where we locate our ball bearing, for example. Okay, and that's where failure will occur. Okay, so the problem with this question is this. Okay, now I'm going to draw the element H. Okay, and I'll draw the orientation. So this is X and this is Y. And now we're going to draw our element. Okay, I will draw. Now the problem is this. Okay. Stress X. This is just an example. Okay. Stress Y. Shear XY is equal to shear YX. I have not a clue, or we have not a clue what all these values are. Okay, not like before. Okay, 100 megapascal, 60 megapascal, 30 mega. We have nothing of that sort. The only thing that we have, okay, the only thing that we have are the torque. Okay, so you see this rotation over here, you have a torque. Over here, you have a point load. And over here, you also have a point load. Okay. So this is a real engineering problem. In fact, you can say that this is like an actual loading situation, which is true. Okay. So now, in carbon fiber, it gets more difficult because we need to know whether we need to know the orientation. Okay, if it's made of just pure metal, the orientation is not important. Okay, for us, it is critical. Right. So now we are going to find. Okay, the first thing we're going to do first is we're going to find. Okay, we're going to find the normal stresses. Okay, stress X and stress Y. Okay, so now I'm going to view. Okay, so as I said, you can download these images on Avenue to learn. So now I'm going to copy. I'm going to copy. If I can find my mouse, my cursor. Sorry. I'm going to make this small, so you can still have a view of it. Right. So this is now my X, Y, and this is our Z. So now I'm going to view this on my YZ plane. Okay. So I'm going to draw now. Sorry, we are going to look at the XZ plane. Okay. So this is our rotation of the Y. Okay. So when we view that, this is what we see. Okay. So this is the shaft. 2, 2, 6, and then 8. Okay. So this is our shaft. And this is where over here, okay, not over there, but this is where we have our element H. Okay, this is our element H. And if we were to look at our loading, This is going up at 600 pounds. This is coming back down at 600 pounds. Okay. And for this structure to be under stress, it has to be fixed. Okay. Why? So this is, it has to be fixed for the structure to see any stress. Why do I say that? Okay. If the shaft is rotating, right, when will it fail? It will only fail if all of a sudden you resist the motion. Yes or no? You all agree? So, for example, if I'm going to jump from the 5th floor of the building, when will I die? So I take a leap of faith, I jump, I hit the 5th, then I go down to the 4th. I'm still alive. 3rd, I'm still alive. 2nd, I'm still alive. When I hit the 1st floor, I die. Any idea why? Any idea why I die on the 1st floor? What is some of you might say, what a stupid question. Anyone can explain to me?
You hit the ground.
Yeah. What happened when I hit the ground?
Sudden deceleration.
Yeah. I'm not allowed to go through any motion. Yes or no? That is why this end, we fix it. Okay. If you allowed it to rotate, right, it won't fail. Right? That's why you don't go from 5th gear and you engage reverse. I dare you. And see what happened. Okay. All of a sudden your shaft is rotating in one direction. All of a sudden you engage reverse. Ay, good luck. Okay. Right. So coming back to here. So we want to find how the stresses are acting on element H. Okay. So one thing I want to highlight, what we are going to find out is we are going to find the moment. Okay. The bending moment. Okay, bending moment. So what do I mean by moment? Let's look at the formula moment. Okay, so moment is equal to force multiplied by perpendicular distance. Okay, moment is force multiplied by perpendicular distance. Okay, so now if we look at the moment down here, right? And we're going to make an assumption. Okay, we're going to make an assumption as what is this assumption? Okay, so if we were to guess, okay, to guess, okay, how will this structure deform? Okay, so the structure will deform, okay, in this direction. Okay, undo. Okay, the structure will deform in this. This is just a guess. Okay, so this is what we call our deformation pattern. Right. So when when the structure is bent this way, it means the moment is going this way. So this is moment about Y. Right. So the counter moment at element H will go this way. Okay, so this is moment about the y-axis at point H. Okay, so we have just applied Newton's third law, action equal to reaction, same in magnitude, different in direction. Okay, so over here, this is our moment vector. Okay, this is our moment vector. The head of the moment vector will always induce compressive stress. The tail end of the moment vector will always induce tensile stress. right? And you can see over here at the top, okay, at the top, you have compression because the circumference